This short video will describe the colligative property called boiling point elevation. The boiling point elevation as a colligative property of a solution goes hand in hand with the vapor pressure depression. That is, when at a particular temperature, the vapor pressure of the solution is less than the vapor pressure of the solvent. Pressure is lower at a given temperature, then you need to raise the solution to a higher temperature in order to bring it up to 1 atmosphere vapor pressure such that the solution will boil. So you can see this boiling point, it's called boiling point elevation, since you have to raise the boiling point of the solution to a higher temperature in order to reach 1 atmosphere for the vapor pressure. Okay, so for the same reason that the vapor pressure is lowered, the boiling point is elevated. And the boiling point is elevated because the solution is now more stable than the vapor. Therefore, the boiling point goes up. And there's a simple equation that relates the change in the boiling point, the change in the temperature, the boiling temperature, to the concentration of the solute in the particular solution in units of mol. And the relationship is the boiling point constant, Kb. This table shows a list of common solvents, the normal boiling points for those solvents, and the mol boiling point elevation constant. Okay, let's take a look at an example. Because the boiling point elevation is a colligative property, the change in the boiling point then depends on the number of solute particles, whether that be a molecule, an ion, or an atom, in the solution, not the type. So therefore, you can not only can you calculate what the boiling point elevation should be based on a given concentration of solute, but you can use data, boiling point elevation data, to determine information about your solute. For example, the molecular weight of a solute. In this particular example, a 2-gram sample of a large biomolecule was dissolved in 15 grams of carbon tetrachloride, a common solvent. The boiling point of this solution was determined to be 77.85 degrees Celsius. Calculate the molar mass of the biomolecule. Okay, now we're going to use the boiling point elevation data to calculate the molar mass of the biomolecule. And so based on the way we're going to do this is based on the boiling point elevation. We're going to calculate the molality of the solution, and then from that we're going to calculate the molar mass of the large biomolecule, because we're given the mass of the biomolecule that was dissolved in a certain amount of solvent. So the change in temperature in this case is going to equal the mol boiling point constant times the molality of the solution. So all we have to do is determine what the change in temperature is, the constant, and then calculate the molality. That information is given in the previous table. The normal boiling point for carbon tetrachloride is 76.5 degrees. So the normal boiling point is 76.5 degrees Celsius. And we see here that this particular boiling temperature for the solution, this is for pure solvent, so for the solution it's 77.85 degrees Celsius. So the change in temperature is 0.85 minus 76.5 degrees Celsius is 1.35 degrees Celsius. Okay, so that's the change in temperature right here. And that's going to equal the boiling point constant, which for carbon tetrachloride from the table is 5.03. Equals 5.03. And the unit there is degrees Celsius, kilogram per mole, times the molality of this particular solution. So we can solve for molality by dividing both sides of the equation by 5.03, and the molality equals, in this case, 0.268 moles per kilogram. Okay. All right. So now that we have the molality, we can use this information that came from the experiment, the boiling point elevation experiment, to calculate the molar mass of the sample. And the way we do this is, since the molality is moles of solute per kilograms of solvent, we know that we have placed 2 gram sample in 15 grams of the carbon tetrachloride, so I can calculate the number of moles present in that 2 gram sample by multiplying by the amount of solvent. So it's going to be 0.268 moles of unknown biomolecule per kilogram of solvent times the amount of solvent, which is 15 grams. Now the unit needs to be in kilograms, so that's 1,000 grams per 1 kilogram. And now we have left units of moles of the large biomolecule, and that's going to equal 0.000402 moles of the large biomolecule. And the molar mass then is just going to be the mass of that large biomolecule divided by the number of moles. So the mass that occupies, that weighs 0.000402 moles is 2 grams. So this can be 2 grams of large biomolecule divided by 0.000402 moles of the large biomolecule, and that gives us a molar mass of 4,975 grams per mole. That's why it's called a large biomolecule. It has a large molar mass.